Hello everyone and welcome to this video where I will start talking about how to measure the enthalpy change using calorimeter. This is a follow-up video of a previous video that we talked about the exothermic endothermic reactions, and we also talked about the enthalpy change. Now there are two types of calorimeters that we can use to measure the enthalpy change. The first type is the constant pressure calorimeter. We usually use this type of calorimeter to measure the enthalpy change of naturalization or dissolution reactions. This type of calorimeter is the simple type of this calorimeter. You can make it out of polystyrene drinking cup with a volumetric flask or metal can inside. You need also a thermometer and a steering rod of glass or metal in order to steer your reaction. You have to remember that you need a stopper, isolating stopper for this system to be a closed system. Now the energy will appear as a temperature, raise in temperature or lowering in the temperature, and we can calculate the enthalpy change using this formula. Delta H is equal minus MC delta T. Now the delta G in that case will be in joules. If you are measuring the enthalpy change or the enthalpy change of 1 mole of your reactants, this means the enthalpy change unit would be joule per mole. Now the mass of the material would be actually the water inside this cup, and you have to remember that the cubic centimeter is equal, 1 cubic centimeter is equal to 1 gram. Now the C in that case would be the specific heat capacity, and the unit is joule per gram per degree centigrade. Temperature would be the temperature difference of the final, T final minus T initial, and this delta T would be in Celsius. Now the second type of the calorimeter is the constant volume calorimeter. We usually call it a bomb calorimeter, and we use it for combustion to measure the enthalpy change of combustion reactions. From the name you could see it will be an isolating metal chamber. Inside this strong metal chamber it will be a liquid and a small chamber. In this small chamber we usually ignite our material, our reactions in presence of oxygen. This is why we need ignition rods or ignition wires to start the reaction. We also need a stirrer to stir the water. This will allow the mixing of the temperature in the whole system and will give us a corresponding temperature change in the temperature. Like the previous case, the change in the enthalpy change would be equal to minus MC delta T. Let's look at one experiment to calculate the enthalpy change of naturalization. In that case, let's look at this example. Place 50 cubic centimeter of 1 mole cubic decimeter per cubic decimeter hydrochloric acid in a cup and record its temperature. This is your initial temperature, so this is initial temperature, and you have to remember this is your concentration. We will use the concentration in order to calculate the enthalpy change of 1 mole of my substance. Now if we placed 50 cubic centimeter, in that case this means it is equal to 50 grams. Then add 50 cubic centimeter of another 1 mole per cubic decimeter, in that case sodium hydroxide. So the reaction or naturalization reaction would start, and for that you need to mix your system, you stir your system, and you wait until you record the highest temperature. Let's assume you recorded your final temperature to be 27.8. Now if I looked at the values that I'm giving here, I also am giving the 50 grams of my alkali. This means the mass of the solution, the total mass would be equal to 50 plus 50, which is equal to 100 grams. Now, if I looked at the specific heat capacity, I will use in that reaction the specific heat capacity of water. The hydrochloric acid and the sodium hydroxide, we will assume that they have the same specific heat capacity of water. This means it would be equal to 4.18 joule per gram degree centigrade. Now, if the starting temperature was 21.3 and this is the final temperature 27.8, this means I have delta H. In that case, would be equal delta T would be equal to 27.8 minus 21.3. This means it will be equal to 6.5 degrees centigrade. Now we can calculate the delta H of my reaction. In that case, it will be equal to minus MC delta T, and let's substitute in this equation. I have here minus and the M is equal to 100, like we calculated the total mass of my reaction. The C, like we said before, is corresponding to the specific heat of water, and the delta T is 6.5. This means this value would be equal to minus 2717 joule. Now we need to calculate the enthalpy change of this reaction in case if I have 1 mole. So we will call it the molar enthalpy. In that case, we need to know the number of moles of my reaction and what happens if we have only 1 mole. So the number of moles would be equal to the concentration multiplied by the volume divided by 1000 to convert the volume into a liter. So I have the concentration, like I've seen in the previous slide, here is equal to 1. So I will multiply 1 multiplied by the volume, in that case was 50, and divide by 1000. This means it's equal to 0.050 moles. So this is the number of moles. So if I have 0.050 mole, this means I got this amount of energy, my enthalpy change. Now, what if I have 1 mole? How much what will be my enthalpy change? So the molar enthalpy change, in that case, this will be called the molar enthalpy change, would be equal to 1 multiplied by minus 2717 divided by 0.050, and in that case it will be equal to minus 54 joule per mole. So now you know the difference between both of those values. This for my reaction, but this one, the molar enthalpy change. So this is the molar enthalpy change. Now let's look at another example, and in this case we will need to calculate the enthalpy change of a combustion reaction. In here, you could see that we used this spirit burner to burn propanol, and we will heat a beaker which is filled with a certain amount of water. Let's say we started with 100 grams. And we need also to know the volume or the grams of my propanol. Let's say we started the reaction and the grams of the propanol was equal to 86.27 grams. And in that case, we will measure the initial temperature of my reaction and the final temperature. So if I started my initial temperature is 20, then we start to combust, to ignite the propanol using this burner, and we will see the amount of heat that will so we need to know the amount of heat that increases the temperature of water. Now I have the final temperature recorded is 30.9, and the mass of the spirit at the end of my reaction is equal to 86.06. This means there is a difference in the grams, which is equivalent to 0.21. This means we burned around 0.21 grams of 1 propanol. So we need also from those to calculate the delta H, and in that case it will be equal to 30.9 minus 20.2. 20.2, and you have to remember one thing: the temperature change will be equal to 10.7, and it have to be a positive value in that case because I have here a combustion reaction. This means energy will be given off, and this energy we will use it to heat the water. Now let's look at the value of the delta H of this reaction. In that case it will be, I will use the same formula, minus MC delta T, and in that case I have the mass of the water, which is equal to 100, multiplied by the C, which is 4.18 for water, and the delta H in that case is equal to 10.7. So this will be equal to minus 4,472.6 joule. Now this amount of energy is released when I burned 0.21 grams of propanol. How much energy would be released for 1 mole of propanol? To be able to know that, I need the molar mass of propanol with the formula C3H7OH. In that case, it will be equal to 3 multiplied by 12 plus 7 multiplied by 1 plus 16 for the oxygen and another one for the hydrogen. The total is equal to 60 grams. This is a molar mass. This is 1 mole of propanol is equal to 60 grams. Now, if I know that this amount of energy is released for 0.21 grams of propanol, so if I have 60 grams, how much energy will be given off? So for that, I will have the delta H in that case would be equal to, I will multiply this value by the 60 divided by the 21. You have to remember, I have to look at it that way. So this is the amount of energy released from 0.21 grams, and in here if I have 60 grams, so how much energy would be given off? So this is the amount of energy would be given off here. I will multiply the minus 4,472.6 by the 60, and I will divide it by 0.21 grams. This is equal to minus 1,300 kilojoule per mole. You have to remember, I converted to kilojoule. This means I divided here also by 1000 to be able to convert it into kilojoule per mole. Now let's look at this example. Calculate the energy transferred when the temperature of 75 cubic centimeter of water rises from 23 to 54. This means an increase in temperature would mean that my delta H is actually equal to a negative value. So this is an exothermic reaction, and if we apply the formula, delta H is equal to minus MC delta T, it would be equal to minus, and the mass in that case I have 75 grams. So cubic centimeter, like we said, is equal to the grams, and here I have the specific heat capacity of water, 4.18, and the difference in the temperature, which would be final temperature minus the initial temperature, which is 23. So I have here the values equal to minus 9,718.5 joule. Now let's look at another example. When 8 grams of sodium chloride is dissolved in 40 cubic centimeter of water, the temperature falls from 22 to 20.5 degrees centigrade. Calculate the energy absorbed by the solution when sodium chloride dissolves. This means I have here the delta H for endothermic reaction, and it must have a positive value. So the delta H in that case would be equal to minus MC delta T, and in here I have minus the mass is 40 grams multiplied by the C with the specific heat of water, which is equal to 4.18, multiplied by the difference in the temperature. You have to remember final minus initial. This means 20.2 minus 22. This will give me a negative value. When I multiply it by this negative value, I will have a positive value to delta H. In that case, it is equal to 250.8 joule. Now, if I need to look at the molar mass of sodium chloride is equal to, so I have here the molar mass of sodium chloride is equal to 58.44 because I have here sodium chloride NaCl. So the Na is equal to 23 and the Cl is equal to 35.5. This means I have here molar mass which is equal to 58.5. So if I have the molar mass, in that case I can calculate the delta H, the molar enthalpy change. So this is the molar enthalpy change would be equal to my molar mass of sodium chloride 58.2 divided by the 8 grams that we dissolved. In that case I have here the 8 grams and multiplied by the delta H of my reaction. This would be equal to 1832.09 joule per mole. Now again I had 250.8 absorbed energy when I dissolved 8 grams. So how much energy would I need to dissolve 58.2 grams? This means I have to multiply the 250 by the 58 and divide them by the 8. Now let's look at this example. A student added 50 cubic centimeter of sodium hydroxide to 50 cubic centimeter of hydrochloric acid. So this is a naturalization reaction. Both solutions were at 18 degrees centigrade at the start of my reaction and the temperature rose to 33 degrees centigrade. Calculate the energy released of this reaction. So again delta H is equal to minus MC delta T, and in that case the M would be the mass of both solution. This means equal to 50 by 50 plus 50, which is equal to 100. And the C, we said that the specific heat capacity of the acid and base, we assume it to be the same as the specific heat capacity of water, and the temperature would be equal to 33 minus 18. Again, the final minus the initial. You have to remember final minus initial. This would be equal to minus 6,270 joule. This amount of energy was released due to this naturalization reaction. By that we came to the end of our video. Until next video, thank you and goodbye.